Now that we've learned some rules for simplifying exponential and logarithmic expressions, we're going to use those to solve some exponential and logarithmic equations and then apply those concepts that we learned, those techniques, to some real-world situations. One of the first rules that we'll use is that if I have log base A of u equal to log base A of v, then I can have u must be equal to v. Now notice that in order for this to work, I have to have the same base, and I also have to have one logarithm on each side. I can't have anything except the two logarithms. So let's look at an equation where I can use this. Okay, now in this equation, I have the same base. There's no base specified, so it's base 10. But I have two logarithms on this side, so I need to combine these two before I can solve the equation. So we're going to rewrite this part using our rules of logarithms as the log of x plus 3 over x minus 1. Okay, now I've met my conditions. I got one logarithm here and one logarithm here. So I just can do without the logarithms and write x equals x plus 3 over x minus 1. I'm going to multiply both sides of this equation by x minus 1 so I don't have the fraction anymore. And then I'll distribute this so I have x squared minus x equals x plus 3. So now this is a quadratic equation, which we've solved quadratic equations before. You get everything over to one side. So now I have x squared minus 2x minus 3 equals 0. I can factor this into x minus 3 times x plus 1. And my result is x equals 3 or x equals negative 1. Now I need to think a little bit about my original equation where I had log of x on the left side. I cannot take the logarithm of negative 1. Logarithm's not defined for negative numbers. So this solution is no good. And this is my only solution. X equals 3. You can verify this solution using a calculator. You can put 3 into your original equation and see how it comes out. But pause the video now and work on checkpoint 1. Here's another rule. If A and U are real numbers and A does not equal 1, then A to the log base A of U is equal to U. So in other words, if I have a logarithm base A, I can eliminate it by raising A to that power. Let's look at an example. Okay, so I have log base 5, which I don't have on my calculator. So to get rid of that log base 5, I'm going to take both of these and make them exponents of 5. So over here I have 5 log base 5, 2x minus 3. And over here I have 5 squared. Well, doing this makes those go away. So now I can write 2x minus 3 equals 5 squared is 25. And now I have a very simple linear equation. And 2x equals 28. So x is equal to 14. Take a quick look back up here. That's not going to cause any problem there. So we're going to take that for our solution. Let's look at another example. Okay, now I've got 2 logarithms here, and so using that technique that we did on the last problem is not going to work out very well. But I am going to move this one over here. Oh, this is 2 minus. So I have log of x minus 16 plus log of x minus 1 equals 2. And this lets me write log of x minus 16 times x minus 1 equals 2. When I multiply this out, I get the log of x squared minus 17x plus 16 equals 2. And now that I have one logarithm, I can use that technique again by making the logarithm an exponent. So up here I'm going to have 10 to the log of x squared minus 17x plus 16 equals 10 squared. So this cancels out. And now I have x squared minus 17x plus 16 equals 100. I move the 100 over here to solve the quadratic equation. So I have x squared minus 17x minus 84 equals 0. This can be factored. If you don't see the factoring, you can always use quadratic formula. But we're going to do x minus 21 times x plus 4 equals 0. So x equals 21 or negative 4. Looking back at my original, I had, log of x minus 16. And if I put negative 4 here, this is still negative, and I can't do that. So negative 4 is not an acceptable solution. And our answer is 21. Okay, and we can put 21 back in our original to verify. So let's work one more example. Log base 2 of x minus log base 2 of x minus 1 equals 1. So we're going to go on just as we did before. We'll rewrite this part as one logarithm x over x minus 1, and then use 2 as a base. So I have 2 to the log base 2 x over x minus 1 equals 2 to the first power. So once more, that cancels out. I get x over x minus 1 equals 2. Multiply by x minus 1. I get x is equal to 2x minus 2. Subtract another x. And I'm going to get x minus 2 is 0, so x equals positive 2. Okay, again, we want to verify that this is a valid solution by trying it out. But you're ready now to pause the video and work on checkpoint 2. We've looked at a couple of techniques now to solve logarithmic equations. Let's look at some to solve exponential equations. Here's another rule. If a to the u equals a to the v, then u is equal to v. So for our first example, we'll do 9 to the x equals 27. I don't have here what I had up here with the bases being the same, but I can get it pretty easily by rewriting 9 as 3 squared. So I'm going to have 3 squared to the x, and 27 is 3 cubed. Now my two bases are the same, so I can eliminate the bases, and I have 2x equals 3, or x equals 3 over 2. Verify that this will work in your original equation. You can put 9 to the 3 over 2 in your calculator and make sure that you get 27. But you can pause the video now and work on checkpoint 3. Here's another rule that we can use. If I have u and r are real numbers, and u is positive, the natural log of u to the r power is equal to r times the natural log of u. This is just our power rule. And although this is written with natural log, I can also work this kind of an equation with common log, base 10, or any other base if I want to. So let's see how this could help us. If I have 3 to the x equals 5. I'm first going to make an estimate. I know 3 to the first is 3. 3 squared is 9. So I would expect my x to be somewhere in between 1 and 2. But let's solve the problem now by taking the natural log of both sides. Okay, once I've taken the natural log, now I can bring this x out front. So I'll put it there instead of here. And now I can isolate the x and write natural log of 5 over natural log of 3. Natural log of 5, natural log of 3, those are both constants, numbers that I can get from my calculator. And when I do that, I get approximately 1.465. And remember I said that we should expect our number to be somewhere in between 1 and 2, and this is. So my answer is at least plausible. And again, I can raise 3 to the 1.465 power on my calculator and see that I get 5. So now you can work on checkpoint 4. In this example, we'll use the power property again to solve the equation. This time I have 3 to the 2x minus 1 is equal to 4 to the x plus 2. I'm going to start by taking the natural log of both sides. Okay, then I move the exponents out front. I'll make this a little clearer. So this is what I have now. We're going to multiply these out. So now I have 2x times the natural log of 3 minus the natural log of 3 equals x times the natural log of 4 plus 2 natural log of 4. Okay, so now I've got two terms here that contain an x and two terms that do not contain an x. So I'll put all my x's on one side. So I'm going to have 2x natural log of 3 minus x natural log of 4 is equal to 2 natural log of 4 plus natural log of 3. Now that I have my x's together, I'm going to factor out that x. So I'm going to have x times 2 natural log of 3 minus natural log of 4 is equal to 2 natural log of 4 plus natural log of 3. Now this looks like I really haven't simplified it much, but in reality I have, because all these natural log of 3, natural log of 4, natural log of 4, natural log of 3, these are constants. I can get those from the calculator. So that's all I need to do. If you want to, you could rewrite this one more time. And have 2 natural log 4 plus natural log 3 divided by 2 natural log 3 minus natural log 4. Now be careful, you cannot cancel out these 2's because the 2 does not apply to these terms over here. So I'm just going to have to put this in the calculator. And I get an answer approximately 4.774. You have some problems similar to this in checkpoint 5. Stop the video now and work on those. Here's an example of an equation that's got a little more complex exponent. I've got 3e to the x squared power equals 600. And the first thing I want to do is this 3 doesn't need to be over here, so I'm going to divide by 3. So that gives me e to the x squared equals 200. And now I'll take the natural log of both sides. In some equations, it doesn't matter if I use log or a natural log, but in this case, because e is involved, I do need to use natural log. So I got natural log e to the x squared equals the natural log of 200. So my natural log and my e cancel each other out. And I get x squared equals the natural log of 200. So then I can write x, I'm going to take the square root of both sides, equals the square root of the natural log of 200. And we'll make this plus or minus. And x is approximately equal to plus or minus 2.302. And you can see in the original equation, it doesn't matter whether we use positive or negative because we're going to square that number and it's going to end up positive. So this is our solution. Go ahead and pause your video and work on checkpoint 6. Now that we've looked at several techniques for dealing with exponential and logarithmic equations, let's look at some practical applications. In our first problem, the number of non-farm jobs in millions added to the U.S. economy by quarter can be approximated by this function. F of x equals 12.1 plus 2.03 times the natural log of x. X equals 1 corresponds to the first quarter of the year 2014. And they said find the first full quarter in which the number of jobs added to the economy exceeded 16 million. So we're going to let f of x equal 16. And find out what x is. But first I want to simplify and get this ln x all by itself. So I subtract the 12.1, which gives me 3.9 equals 2.03 natural log of x. And then I'm going to divide both sides by 2.03. And I get natural log of x is 3.9 divided by 2.03. So now I'm going to take this equation and use it as exponents for e. I'm gonna flip the equation over so the natural log is on the left. Okay, and as before, this and this are going to cancel out. I get x is equal to e to the 3.9 over 2.03, and x comes out to approximately 6.83. Now I need to pay attention to the question which asks, what's the first full quarter that the economy jobs exceeded 16 million? Well, we see that it happened in quarter 6.83, but since I'm on a full quarter, I'm going to round that up to x equals 7. So if x equals 1 was the first quarter of 2014, x equals 7 would be the third quarter of 2015. So work another problem like this in checkpoint 7. Here's another practical application problem. The amount of money U.S. consumers spend online for food in billions can be approximated by this function. F of x equals 0.174, 1.318 to the x power. And x equals 11 is the year 2011. And I want to know, if this model remains accurate, what's the first full year in which online grocery sales exceeded 50 billion? Okay, so I want f of x to be 50 billion I'm going to start by dividing by 0.174. And then take the natural log of both sides. I have the natural log of 50 over 0.174 equals the natural log of 1.318 to the x power. And since this is now a logarithm, I can move the x from exponent and bring it out front here like that. So now to solve for x, I'm going to divide by this. I got the natural log of 50 over 0.174 divided by the natural log of 1.318 equals x. And when I put that all in my calculator, I get an answer of approximately 20.5. Well, we were told that x equals 11 was 2011, so x equals 20.5 would be 2020, but it's not a full year, so I need to round it up again and say that the year is 2021. Okay, you're going to work this problem again in checkpoint 8. Next, we're going to work a problem that has to do with half-life. Half-life is the idea that some radioactive substances lose half of their mass in a specified period of time. Scientists use this quite a bit to do carbon dating, where they measure the amount of carbon-14 in some natural substance that had carbon-14 in it while it was alive, but then stopped maintaining carbon-14 when the organism died and started losing it. This is something that can be measured and is used to date how old the remains of living things are. So let's take a look at this problem. It says, a round wooden table hanging in Winchester Castle in England was alleged to have belonged to King Arthur, who lived in the 5th century. A recent chemical analysis showed that the wood had lost 9% of its carbon-14. How old is the table? And we're given this equation for decay of carbon-14. Okay, T equals 0 corresponds to the time of death, and in this case that's the time that the wood used to construct the table was cut down. So let's look at this equation. It said it's lost 9%. Our problem tells us that f of t is 91% because 9% has disappeared. So we're going to write f of t as 0.91 of y sub 0, the amount we had at the beginning. 9% is gone, 91% is left. Then I have y sub 0 times 5 to the t over 5730. So these y sub 0's cancel out. And I get 0.91 equals 5 to the t over 5730. Now I'm going to take the natural logarithm both sides. Natural log 0.91 equals natural log 5 to the t over 5730. Now that this is an exponent of a logarithm, I can bring it out front. So let's do that. I get natural log of 0.91 equals t over 5730 times the natural log of 5. Okay, divide by the natural log of 5. So these are going now. And I got this amount, natural log of 0.91 divided by natural log of 5 equals t over 5730. So now I'm going to multiply by the 5730. So this all can go in my calculator, and it gives me a result of approximately 779.63. So the table is about 780 years old. Could not possibly have belonged to King Arthur because this was in the 1300s or 1400s. Much too late for King Arthur. You'll work another problem using carbon dating formula in checkpoint 9. Our last example deals with the Richter scale, which is a scale that's used to measure earthquakes. So here's the example. The intensity R of I of an earthquake measured on the Richter scale is given by this equation. R of I is the log of I over I sub 0. And I is the motion intensity, and I sub 0 is the motion intensity for the smallest measurable earthquake. And this is the standard that we use to measure other earthquakes. We talk about the smallest measurable earthquake. The underwater earthquake that caused the disastrous 2004 tsunami in Southeast Asia measured 9.1 on the Richter scale. How did the ground motion of this tsunami compare with that of the zero earthquake? So using our equation, we've got that R sub I, or R of I, is equal to 9.1. That was the measurement. So we've got now the log of I over I sub 0 is equal to 9.1. By the definition of logarithms, 9.1 is the exponent to which 10 must be raised to produce this. So I can say I over I sub 0 is equal to 10 to the 9.1 power. Or we could also write I is equal to 10 to the 9.1 times I sub 0 is another way to write that. So 10 to the 9.1 is approximately equal to 1.26 billion. So the tsunami quake was 1.26 billion times more intense than the smallest detectable quake. Okay, another question now. What is the Richter scale intensity of an earthquake with 10 times as much power as the 2004 tsunami earthquake? So we're going to say the intensity is 10 times as much as our 10 to the 9.1 times I sub 0. So this is going to be then just 10 to the 10.1 I sub 0. So the Richter scale measurement would be 10.1. So you can see here that Going up one number on the Richter scale means the quake is 10 times more intense. And this was why if you talk to people who live in earthquake zones, and they'll tell you, you know, a 3 is no big deal, but a 5 is 100 times more intense than a 3. You know, it sounds like, well, it's two more, but it's 100 times more. And a 7 then would be 10,000 times more than a 3. So the intensity goes up pretty rapidly. There's another Richter scale problem in your checkpoints. It's the last one for this section, and then you'll be ready to go on to your homework.